Hello, my name is Jeferson Gonzalez-Gomez. I'm a PhD student at Karlsruhe Institute of Technology in Germany, and today I will present you with our work titled Smart Detection of Obfuscated Thermal Covert Channel Attacks in Mini-Core Processors. As you may know, a thermal covert channel is a stealthy communication channel between two malicious applications via controlled CPU activity. The first application, known as malware, takes the role of a transmitter, while the second application, the spy, acts as a receiver. As we can see in the figure, when the transmitter wants to send a bit of 1, it does some processing which hits its core. Because of heat transfer, this temperature increase will be noticeable in the core where the receiver application is executing. By reading the thermal sensor of its own core, the receiver is able to detect the temperature change and decode the bit sent by the transmitter. This is how communication can be done via temperature variations. To understand the motivation of our work, let's first look at the background of thermal covert channel detection. Traditional detection techniques for thermal covert channels employ the performance of a core in instructions per second or cycle, combined with the discrete Fourier transform technique to detect attackers. Here, in the figure, we can see the DFT spectrums of the core IPS for two applications. The one on the left belongs to a regular benchmark application, and the one on the right comes from a traditional attack. To differentiate between the attacker and the normal application, one could use a simple threshold heuristic. By setting a threshold of 300, marked here as row 1, one can detect the attacker since it has components with a magnitude higher than this value, while the normal application does not. However, as it was pointed out recently, this solution does not work very well with different attacks. This is the case of the so-called stealthy attacks, where the transmitter intentionally reduces the processing time to encode the bits in order to reduce the magnitude of its DFT. As seen from the new figure, the spectrum does not have magnitudes greater than the threshold, hence it would not be detected as an attack. One simple solution to this problem would be to create a new threshold, row 2 as shown now. This would work for both attacks. But, as we can see in the upper left figure, it would fail for the normal application, as it has components greater than the threshold and it will be misclassified as an attacker. This means that simple heuristics do not work well for the variety of attacks. To solve this issue, a recent approach proposed to use the shape of the DFT, meaning the peaks and small side lobes marked here in the figure, as a feature for a machine learning-based detection. However, this solution assumes the spectrum of all the attacks to contain these features. This is not the case for our new obfuscated short-duration attacks, which will be described further in this video. As it can be seen on the new figure, the shape of the DFT of this new attack is very different from the others. There are no visible side lobes, and the spectrum resembles much more to a normal application than to the other attacks. This, as I will show in the evaluation, means that the DFT-based solutions really struggle when dealing with new attacks, especially ones of short duration. As shown in the previous motivational example, the DFT-based detection solutions for thermal covert channels struggle with some attack variants, such as obfuscated short-duration ones. This translates into low detection accuracy, which is potentially dangerous for the system. To tackle this problem, in this work we present the following contributions. First, we propose a new obfuscated short-duration attack, which manages to stay undetected under the state-of-the-art techniques. Then, we show how DFT-based solutions deteriorate when facing short-duration attacks. Finally, we propose DOTECA, a smart thermal covert channel detection technique. By employing windows of time domain measurements, we are able to obtain high detection accuracy for all types of attacks. Furthermore, we show how our detection solution produces very low overhead in comparison with other existing approaches. To begin with our contributions, let's start with our new obfuscated short-duration attack. In summary, the attack is divided into two segments, transmission and obfuscation. The transmission segment, shown on the left part of the figure, is a short-duration communication where packets are encoded and sent via temperature variations. This takes 25% of the time of the attack. In the obfuscation segment, shown in the right, the malware application behaves like a normal processing application to avoid detection. In this example, we employed black holes from Parsec as the processing kernel. The obfuscation segment takes the remaining 75% of the time. As I will show later, this obfuscation allows our attack to remain undetected under DFT-based detection solutions. Now, in the figure on the right, we can see how the transmitter and the receiver applications are designed. In the transmission, the data to be sent is encoded using Hamming as error correction code. Then, a header is appended to the binary data. Afterwards, a processing kernel takes the binary data and applies a modulation scheme consisting of the return to zero encoding as well as an on-off keying. After the transmission duration has expired, the duration control switches to the normal processing kernel for the remaining duration. On the receiver side, the application filters, demodulates, and deserializes the data. After it finds the appropriate header, it decodes the packet and extracts any possible errors using Hamming. Now let's take a look at an overview of Doteca, our smart detection technique for thermal covert channel attacks. Doteca is a machine learning based solution which employs time domain measurements of a core performance in instruction per second as input to a neural network model. At the same time, we collect traces from different attacks as well as normal benchmark applications. We separate these traces in windows of 100 samples to form a dataset. The window length of 100 samples is chosen to quickly capture the periodic behavior of the attack, even under short duration transmissions. We employ this dataset to train our model. At runtime, every 1 millisecond, we take IPS samples from a core and form a window of measurements of 100 samples. Then we invoke our model using the collected window as input and perform the prediction of whether the traces belong to a normal application or to an attacker. Note that Doteca is a distributed mechanism, where an individual instance of the same model is invoked per each core. At runtime, every 1 millisecond, we take IPS samples from a core and form a window of measurements of 100 samples. Then we invoke our model using the collected window as input and perform the prediction of whether the traces belong to a normal application or to an attacker. Note that Doteca is a distributed mechanism, where an individual instance of the same model is invoked per each core. Here we can see the experimental setup employed for owl evaluation. We used HotSniper, an integration of the commonly used sniper simulator with Hotspot for temperature modeling. We used the Gainsdown model for the CPUs as depicted. We run the attacks and benchmark applications with CPUs at different frequencies varying from 1 to 4 GHz. For the attack, the transmitter and the receiver cores are always at a 1 hop distance from each other. The transmission frequencies for the channels vary from 30 to 350 Hz. To evaluate the effectiveness of our new attack, we first transmit 1000 bits in 10-bit packets at a local transmission rate of 20 bits per second, which transforms to 5 bits per second due to the obfuscation. As it can be seen from the results, we achieve a very low bit and packet error rates of about 1%. Then, to show how our attack evades the DFT-based detection mechanisms, we implemented a baseline of 2 solutions from the state-of-the-art, the simple threshold-based detection and a recent neural network-based one. As seen from the figure, the detection accuracy massively drops to less than 20% when evaluating against our new attack in comparison to the baseline. Now, we perform different experiments to evaluate our solution in comparison to the recent NN-based solution from the state-of-the-art. In the first experiment, we train and evaluate the models using traditional attacks and benchmark traces. As expected, both models show very high detection accuracy. In experiment 2, we keep the same training dataset but evaluate against stealthy attacks, which were unseen during training. As it can be seen from the figure, our model was able to generalize to the unseen attacks with a high accuracy, but the state-of-the-art solution was not. Similarly, in experiment 3, we keep the same training dataset, but now evaluate against our short-duration attacks. Once again, our model was able to generalize greatly to this new attack variant, but the state-of-the-art solution failed to do so. In summary, when training only with traditional attacks, our time domain solution is much better at generalizing to the unseen variants than the DFT-based approach. Now, for the remaining experiments, we expand the training dataset to include information about other attacks. In experiment 4, we train and evaluate with traditional and stealthy attacks, as well as benchmark traces. Here, both models perform very well. In experiment 5, we keep the same training dataset, while evaluate against our new attack, which was not seen during training. Once again, we can see how Doteca keeps a very high accuracy, while the accuracy of the state-of-the-art solution massively drops. Finally, we expanded the state-of-the-art model by including traces from our new obfuscated attack in the training. As shown, even when the traces were seen during training, the accuracy of the state-of-the-art model still drops about 20%. Notably, the DFT-based approach not only was not able to generalize to new attacks, but really struggled with the short-duration attack, even when trained for it. On the other hand, during all experiments, our time-based model kept a very high accuracy of over 95% even under unseen scenarios. This reflects how the time analysis is better than the DFT when evaluating against a wide variety of attacks. Our last experiment is regarding system overhead. Again, we compare against the recent DFT-based approach in the state-of-the-art. In summary, when measuring the data collection time plus the inference of the model, we produce up to 14 times less overhead than the reported DFT-based approach. To conclude, in this work we proposed a new obfuscated short-duration attack that managed to remain undetected under existing detection approaches. Then we have shown how DFT-based solutions struggle when facing new attacks, especially those of short duration. And finally, we showed the TECA, our time-domain machine learning-based solution, which was able to detect all variants of the attack with very high accuracy, while producing much less overhead in the system than the recent counterpart. With this, I conclude my presentation. Thank you very much for your attention.